Welcome back to Talk Tensors, the show where we dissect the most intriguing machine learning papers. Today, we're going to be taking a deep dive into can MLLMs reason in multimodality, an enhanced multimodal reasoning benchmark.
Yeah, this paper is really digging into something pretty fundamental in AI. Can these big multimodal large language models, or MLLMs for short, can they actually reason, like not just process information, but really solve problems using both text and images?
It's kind of like we're finally testing if AI can tackle those classic puzzles, how many triangles are in this picture kind of thing. But obviously, we're talking way more complex stuff here.
Exactly. The researchers behind this paper are arguing that the benchmarks we've been using, well, they're just not tough enough anymore. They either lean way too heavily on text or the visuals are just way too simple. So they've gone ahead and created this brand new benchmark called AIM-MA, and this is designed to really push these MLLMs to their limits.
So before we get into the nitty-gritty of Emma, maybe it'd be helpful to take a step back and, look at the bigger picture here. What kind of led to this need for a more, hardcore multimodal reasoning benchmark?
It's been a pretty wild ride, actually. Like way back, those early AI models were mostly text-based. They were all about things like natural language processing. Then we saw this huge surge in computer vision where models were learning to, actually see and interpret images. But the real turning point, the real game changer, has been these multimodal models that are popping up. They're trying to bridge the gap between language and vision.
So basically, we've gone from AI that could just read to AI that could actually see. And now we're on this quest to create AI that can understand the world through both.
Yeah.
Like it's almost as if we're trying to teach a machine to read Braille with one hand while interpreting like a Picasso painting with the other, all at the same time.
Yeah. That's a fantastic analogy. And the real challenge isn't just processing these two types of information separately, but actually integrating them, using them together to solve these really tricky problems. Think about how we use a map to navigate, reading the street names while picturing the route, or how we can visualize a room just from a written description in a book.
Right. We're constantly blending visual and textual information without even realizing it. So how does MA play into all of this?
Well, think of Emma as the ultimate test for these multimodal models. It's specifically designed to assess how well they can actually reason across these modalities. They're thrown right into the deep end with challenges in math, physics, chemistry, even coding.
Okay, I'm already starting to feel a little overwhelmed just hearing about it. Tell me more. What sorts of problems are we talking about here?
I mean, imagine an AI having to figure out how to rotate shapes in its, mind, I guess, to solve a geometry problem. Or maybe trace the path of light through a bunch of refractions, but it only has a diagram to go off of.
That sounds pretty darn tough, even for a human, I'd say. What about these chemistry and coding problems? What do those look like?
Those are no walk in the park either. You might have an AI trying to decipher those crazy arrow-pushing diagrams you see in organic chemistry, predicting how a molecule is going to change after a reaction. Or maybe it has to pick the right code snippet to generate a specific type of data visualization.
So we've got this multimodal obstacle course set up with EVA. But the real question is, how did these AI models actually do? Did any of them manage to, conquer this thing?
Well, the researchers put 9 of the top MLLMs through their paces, some real heavy hitters like GPT-4, Claude, Gemini. And the results were, kind of surprising. Even the best model out of the bunch only managed to score 45.75% on EMA. That's like a balanced subset of the full benchmark.
Yeah, that's not exactly a stellar grade, is it? Especially when you compare it to how humans did.
Right. Human experts, these are the folks who are basically masters of multimodal thinking. They aced it with a score of 77.75% on that same subset.
So there's still a pretty significant gap between us mere mortals and our AI counterparts when it comes to this kind of integrated reasoning.
Yeah.
I'm curious, though, were there any unexpected findings in how these different AI models performed?
What really stood out to me was how chain of thought prompting, or COT for short, affected different models. COT is this technique where you basically force the model to think step by step, kind of like how you'd write out a solution to a math problem.
Oh, so you're giving the model a little extra help, some scaffolding to structure its thought process, so to speak?
Exactly. And for some of those closed source models, COT actually gave their performance a little boost. But here's the interesting part. For the open source models, it actually made things worse.
No, that's fascinating. Why would that happen? Any ideas from the researchers?
It seems like maybe At least in their current form, open source models might not be quite as good at using language to help them solve visual problems. It's almost as if they haven't quite figured out how to connect those two worlds as effectively as those closed source models.
That definitely brings up some interesting questions about how these models are designed, how they're trained. Seems like the secret sauce might not just be raw computational power, but also this ability to weave together different ways of thinking.
Absolutely. And I think it really underscores just how complex this task we're asking these models to do is. Teaching a model to recognize objects in an image, that's one thing, but teaching it to actually reason about those objects, to understand how they relate to each other in space, their physical properties, how they interact, that's a whole different ballgame.
It's like we're not just asking them to see the pieces on a chessboard, but to actually understand the rules of the game and plan out a winning strategy.
Exactly. Now, the researchers didn't just stop at COTI, they also explored something called test time compute scaling.
I gotta admit, that one sounds a bit intimidating. What exactly is test time compute scaling? Break it down for us.
It's actually a pretty straightforward idea. Imagine you're reading a really dense passage and you have to reread it a few times to really grasp it. Test time compute scaling is kind of like that for AI. It's like giving the model multiple chances to process the information and refine its answer. So instead of just one shot at the problem, it gets multiple tries.
So it's not about tweaking the model itself, but more about giving it more time and resources to work through the problem. Did that help at all?
To a degree, yes. But even with this extra processing power, the AI models still couldn't quite reach that human level performance. It seems like there's something more fundamentally different about how we as humans approach these tasks compared to how AI does.
Which leads to a really important question. What exactly is tripping up these AI models? What are those specific roadblocks that keep them from reaching that human level of performance on these multimodal reasoning tasks?
The paper's error analysis gives us some clues here. It looks like AI models often stumble when they're faced with tasks that involve spatial reasoning, being able to mentally manipulate what they're seeing. It's almost like they can recognize individual elements but have trouble understanding how those elements relate to each other spatially.
Could you give us an example of what that might look like in the context of NA?
Sure, let's say you've got an AI that's trying to crack a physics problem where it needs to figure out the direction of a force based on a diagram. It might get the concept of force, but actually visualizing how that force would act on the object in three-dimensional space. That's where it struggles. Kind of like trying to solve a jigsaw puzzle when you can only see a few pieces at a time.
Reminds me of that classic experiment with kids and a dollhouse,
Yeah.
where they're shown a dollhouse and then asked to find a hidden toy based on a picture of the dollhouse from a different angle. Little kids often have a tough time with that because their spatial reasoning skills aren't fully developed yet.
Exactly. It seems like AI models are facing a similar hurdle when it comes to visual reasoning. They can pick up the individual pieces, but struggle to mentally rotate, translate, and manipulate them to solve those spatial problems.
So the takeaway here is that even though AI has come a long way in areas like natural language processing, visual and spatial reasoning are still major challenges.
Precisely. And it's not just about recognizing objects or understanding words in isolation. It's about integrating those different modalities, building a mental model of the world that allows AI to truly reason about what it sees and hears.
I'm starting to see why this paper is such a game changer. It's not just about testing the limits of current AI, but about pinpointing those key hurdles we need to overcome to really unlock the full potential of artificial intelligence.
Absolutely. AIMA gives us a new benchmark, a new yardstick to measure progress in multimodal AI. And these findings really highlight the need to move beyond just data-driven approaches and start exploring new architectures, new training methods that specifically target those spatial and relational reasoning skills.
So it's not just about throwing more data at the problem, but about finding smarter, more innovative ways to teach these models to think like humans, to see the world not as a bunch of pixels, but as this dynamic, interconnected web of relationships.
Exactly. And that brings us to our novel notions segment, where we take the ideas from the paper and sort of, extrapolate a bit. This paper was all about evaluating existing models, but the question now is, how do we actually improve those multimodal reasoning abilities?
That's a great question. What are some of the research directions you see emerging from these findings? So how do we actually get these models to think more like us when it comes to this visual reasoning stuff? What are some of the things researchers are trying out?
One really promising approach is to start incorporating more structured knowledge into how we train these models. So instead of just feeding them raw images and text, we can actually give them explicit information about spatial relationships, object properties, the laws of physics, that kind of thing.
So it's like giving them a textbook on how the world works, rather than expecting them to learn everything just from looking at data, right?
Exactly. And there are a bunch of different ways to go about this. We can use things like graph neural networks to represent knowledge as this interconnected web of concepts, or we could even borrow techniques from symbolic AI to encode logical rules and constraints.
So instead of just learning patterns from data, they'd actually have some foundational understanding of how things work, which would hopefully make them better at reasoning about new situations.
Right. And another interesting avenue is to explore new architectures, specifically designed for multimodal reasoning. Like some researchers are experimenting with models that have separate modules for handling visual and textual information. But the key is that there are mechanisms to kind of dynamically integrate these representations based on whatever task the model's working on.
So it's almost like having specialized teams, one for vision, one for language, but with a really strong communication channel between them so they can collaborate effectively.
Exactly. And another really cool approach is to take inspiration from the human brain itself. Cognitive scientists have been studying how we develop spatial reasoning skills for decades, and there are some really valuable lessons we can learn from their work. For example, we know that kids learn best through hands-on exploration and play. They build these mental models of the world by manipulating objects, trying out different perspectives, and getting feedback on their actions.
So it's not enough for the models to just passively absorb information. They need to actually engage with their environment, learn by doing, just like we do.
Absolutely. And that's actually led to some really exciting developments in AI, like reinforcement learning and simulation-based training, where models can interact with virtual environments and get rewarded for solving spatial problems.
So it's almost like training an AI to play a video game, where the goal is to solve puzzles and navigate these complex environments.
You got it. And by incorporating these game-like elements into the training process, we can encourage the models to develop more robust and flexible spatial reasoning abilities. Because in the end, the goal is to create AI that can not only recognize patterns, but really understand the world around them, just like we do.
So it's not just about building machines that can beat us at chess or process information faster, right?
Yeah.
It's about building machines that can think with us, work alongside us, and help us solve some of the biggest challenges we face.
Couldn't have said it better myself. And this whole area of research into multimodal reasoning, well, I think it's a vital step in that direction.
Well, I think our listeners definitely have a lot to think about after this deep dive into the world of multimodal AI. It's clear that we're still in the early stages, but the progress is truly exciting.
It really is. And as researchers keep pushing the boundaries, I have no doubt we're going to see even more amazing breakthroughs in the years to come.
And that's all the time we have for today's episode of Talk Tensors. Be sure to check out the show notes for links to the paper we discussed and some other cool resources. And as always, keep those neural networks firing, and we'll catch you next time.